Welcome to Quickly Quantum, Episode 1. Quantum computing is having its moment. Billions of dollars moving, governments picking sides, and a hype machine running at full volume. This show exists to cut through all of it. Here's the deal. Every weekday, in about 10 minutes, I'll bring you the quantum news that actually matters. The breakthroughs, the money, the policy, in plain English. You don't need a physics degree to be here, and if you have one, stick around anyway. The analysis is where we earn your time, and every main story ends with the hype check, my blunt 1 to 10 call on how much substance is under the headline. Saturdays, we recap the week and rescue the stories that slipped through the cracks. Sundays, we slow down and take one big question apart, with every side of the argument represented. And some transparency, because that's the whole brand. I'm Brian Lampert. This show is voiced by an AI clone of my real voice, built and run by me, and every episode is fact-checked against live sources before it reaches your ears. When I'm giving you opinion instead of news, I'll tell you. That's the show. Let's make episode 1 count. Here's a sentence you don't hear every day. A hospital, a national lab, and a computer company just teamed up to help solve fusion energy's fuel problem. This is Quickly Quantum, your daily brief on the quantum frontier. It's Monday, July 6th, 2026. Let's get into it. First, money. Qolab, the superconducting quantum hardware startup, closed a Series B worth $54.2 million. The round was led by UC Investments, with the Wisconsin Alumni Research Foundation, Octave Ventures, and Phoenix Venture Partners also chipping in. What makes Qolab interesting isn't just the cash, it's the pedigree. The company was co-founded by John Martinez, who won the 2025 Nobel Prize in Physics, alongside former Google quantum executive Alan Ho. Their pitch is building fault-tolerant superconducting processors, quantum chips designed to survive errors instead of just tolerating them badly, using the same manufacturing discipline you'd find in a semiconductor fab. On X, Jesse Landry, founder and CEO of DevCuration, put it this way, quote, "Quantum is leaving the science project phase. The next quantum winners will not just prove what is possible in the lab. They will make qubits reproducible, manufacturable, and reliable enough for the market to finally scale." End quote. That's the bet anyway. Whether Qolab is one of those winners is a multi-year question, but the $54 million says some serious investors think it's worth asking. Meanwhile, zoom out from Qolab and you see the same story at industry scale. McKinsey's Quantum Technology Monitor for 2026 dropped a number that stopped me cold. Private investment into quantum startups hit $12.6 billion in 2025, 6.3 times what it was in 2024. And here's the flip side of that coin. Government money's share of total quantum funding collapsed from 33% down to just 3% in a single year. As independent analyst at Global Investor summarized on X, governments walked away while private capital surged in, with 90% of that money landing specifically in quantum computing rather than sensing or networking. Now, a quick honest note here. This report itself dates back to April. Its numbers are just getting freshly recirculated across outlets this week. But the underlying trend, grants giving way to equity stakes, is real, and it's reshaping who calls the shots in this industry. When private money dominates, the pressure to show near-term returns goes up. Keep that in mind because it's going to matter again later in the episode. Speaking of big money moves, Keyfactor announced a strategic growth investment north of $1 billion from Summit Partners. Keyfactor is the company behind a lot of enterprise cryptographic discovery and public key infrastructure tools, and it was already valued near $1.3 billion after a prior investment from Sixth Street Growth plus a run of acquisitions. This new money is earmarked to scale up its post-quantum cryptography business, the encryption standards designed to survive an attack from a future quantum computer. It's a reminder that the quantum threat to today's encryption isn't some distant sci-fi worry to institutional investors. It's a line item people are writing billion-dollar checks against right now. And in hardware infrastructure, IBM is asking Dutchess County's Industrial Development Agency for financial incentives to build its next-generation quantum manufacturing site in Poughkeepsie, New York. We're talking about a 511,000 square foot facility meant to produce IBM's Starling and Blue Jay fault-tolerant systems. Its roadmap toward quantum computers that use logical qubits, meaning error-corrected qubits built from many physical ones at real scale. Local officials have already flagged that the project needs grid capacity verification because cooling a quantum computer down to near absolute zero, which is what these superconducting chips require, draws an enormous amount of power. $2.5 billion is the number attached to the build. That's not a science announcement, that's industrial policy, and it tells you IBM is planning for a future where it needs a lot more quantum chips coming off a line, not just out of a lab. Our main story today keeps us with IBM, but pairs it with two names you don't usually hear in the same sentence: Oak Ridge National Laboratory and the Cleveland Clinic. Here's what happened. A team from Oak Ridge, Cleveland Clinic, and IBM used a quantum computer to calculate 9 different molecular configurations of a material called FLiBe. That's a liquid salt made of fluorine, lithium, and beryllium. According to the article covering the work, this is the first known instance of these kinds of calculations being run on quantum computers. FLiBe matters because it's one of the leading candidate materials for fusion reactor breeding blankets, the components inside a fusion reactor that are supposed to catch neutrons flying out of the fusion reaction and convert them into tritium, the rare fuel that most proposed fusion reactors actually need to run. And tritium is the bottleneck. It barely exists in nature. If you want fusion power plants running at scale, you need a reliable way to breed your own tritium fuel inside the reactor itself, and that means understanding exactly how FLiBe behaves at the atomic level, how it binds tritium, how it holds up under extreme heat, intense neutron radiation, and magnetic fields. That's a brutal material science problem, and until now, understanding it has meant either expensive physical experiments or classical computer approximations that, frankly, aren't precise enough. So what did the quantum computer actually add? The team used what IBM calls quantum-centric supercomputing, pairing a quantum processor with classical CPUs and GPUs, so the parts of the calculation that involve tricky quantum mechanical behavior of electrons run on the quantum hardware, while the rest runs classically. This is the same general technique the group has used with Cleveland Clinic to simulate proteins spanning 12,635 atoms. Applying it here let them nail down the electronic structure of FLiBe with more precision, specifically how strongly its atoms grab onto tritium. Tom Beck at Oak Ridge framed this as part of something much bigger, a coalition spanning 7 Department of Energy national labs, 4 universities, 3 industry partners, and Cleveland Clinic, all working under the DOE's Genesis mission to unify quantum computing, AI, and classical supercomputing to accelerate scientific discovery. Kenneth Mers at Cleveland Clinic called it an extension of their biological simulation work into materials science. And IBM's Jerry Chow, who leads quantum-centric supercomputing there, said these results add to, quote, mounting evidence that quantum-centric supercomputing is now a practical scientific tool, end quote. Now here's my read. I want to be excited about this one, and there's real substance here. It's a genuine cross-institutional collaboration, published on arXiv, independently picked up by multiple outlets the same day, including IBM's own newsroom and HPC Wire. That's not nothing. But let's be precise about what was actually shown. This is a chemistry simulation demonstration. It is not a claim that a quantum computer did something a classical supercomputer fundamentally could not do. The release doesn't establish quantum advantage here. It establishes that quantum-centric supercomputing can produce these calculations, not that it's the only way to get them, or even necessarily the best way, yet. And it's worth noticing the timing. This lands the same month IBM is asking Dutchess County for tax breaks to build a $2.5 billion quantum manufacturing campus for its fault-tolerant roadmap. A cross-institutional science story involving a beloved hospital system and a national lab working on clean energy is, let's be honest, also a very good look for IBM's quantum business right when it needs public and investor goodwill for a massive capital project. That doesn't make the science fake. It does mean I'd read the press release with the same skepticism I'd bring to any co-branded announcement. Genuine research wrapped in a moment of very convenient marketing timing. What would change my mind that this is more than a nice demo? A direct apples-to-apples comparison showing the quantum-centric approach beating the best classical methods on accuracy or speed for this exact FLiBe problem. Right now, that comparison doesn't exist in what's been published. Until it does, the practical payoff for actual fusion reactor design is likely still years out. Time for the hype check. I'm putting this one at a 5. Real collaboration, real institutions, a genuinely hard materials problem tackled with a legitimate technique. But no quantum advantage claim, no classical comparison, and a publication timeline that suspiciously flatters IBM's capital raising moment. Solid science, oversold packaging. That's Quickly Quantum for today. New episodes every day. This is an AI-voiced podcast created and built by a real person using today's cutting-edge technology. I'm Brian Lampert. See you tomorrow.